Okay, welcome back to this video about lubricants. This part 2, I will talk about additives to lubricants. You must excuse me, I'm a mechanical engineer originally and I'm not a chemist, so I may treat the chemistry in a little bit rough way, but I'm doing this from a kind of practical engineering perspective, so please bear with me. Let's start discussing how a molecule interacts with the surface. It may adsorb on the surface with two ways, or it can react with the surface. The adsorption processes are normally separated in two categories: physisorption, where you have weak interaction, weak bonds between the molecule, the polar molecule on the surface, and chemisorption, when you have a strong bond between the molecule and the surface. In chemical reaction, then the actual molecule reacts with the surface and forms a new material here on top of the surface. Typically, friction modifiers are of this category, works with this in this way, physisorption, while EP additives are typically of this type. EP is to reduce the risk of scuffing, while the anti-wear additives are maybe a kind of combination of chemisorption and chemical reaction. So those already mentioned additives are some kind of tribo-improvers. They improve the tribology. The friction modifiers, as I said, working with physisorption, the weak van der Waals bonds, they repel the other surface. The hydrocarbon tails repel hydrocarbon tails on the other surface. So it forms a kind of carpet of molecule tails here that carries some load. So if the conditions are not too severe, they definitely lowers the friction. The extreme pressure additives then, they form when the temperature becomes high, so extreme temperature additives would be better. They reacts with the surface and forms, instead of forming an oxide layer, you form the sulfide layer. So, and that reaction is faster than the oxide formation. So this is useful when you have very high PV numbers, when you have a lot of energy, when you have a big risk of scuffing or seizure. So you form this as sacrificial layer of iron sulfide in this case. But that also means that you have a corrosive process. You take iron from the surface, form a sulfide, and wears it off, and then it's a kind of tribo-corrosive process. But it's better to have that than having a scuffing or seizure. So you have to choose in between two bad things in this case. And then the third category of tribo-improvers is the ZDDP, typical example of an anti-wear additive. And the anti-wear additive ZDDP is very commonly used. The molecule looks like this. So you have zinc, you have sulfur, you have phosphor in it, and you have some hydrocarbon tails. And its full name is zinc dialkyl-dithiophosphate. So it reacts with the surface and the base oil, and it's activated by the tribo energy and the high PV numbers. So it forms this tribo film, and it's often said to be a smart film because it's pretty hard and wear resistant down here, where you have zinc iron phosphates, and then it becomes softer up here, and that means that it's soft here, so it doesn't damage the counter surface, and so it's softer than the steel, and the thicker it is, the softer it will be, and the less wear resistant it will be. So it wears off all the time. So it's a kind of a sacrificial layer in this case too, but it's then constantly reformed again But that means also that you consume the CDP. But this is a very useful additive, and it definitely stops the wear process significantly. In the future, you may not have metals like zinc in an additive, so there is a need to make ash-free lubricant additives for the future. But at the moment, this is a very commonly used CDP additive. There are so many other additives inside the lubricant. One type is rheology improvers. That they are not surface active in this case. They just they are active in the bulk of the fluid. So one type is viscosity index improvers. You have that in multigrade motor oils, for example, because back in the days you actually used one winter oil and one summer oil because the viscosity was varying so much with temperature. But by using the VI improvers, you can have a multigrade oil, and that means that you reduce the influence of temperature on the viscosity. And it's called VI improvers, viscosity index improvers, because viscosity index is a measure of the influence of temperature on temperature. It's a very strange number. There are some two reference oils, one with very good or low dependence on temperature, and one with very poor dependence. But nowadays we have many multigrade oils with higher VI than 100. So I would say this is a poor measure, but still it's used, and still it's named VI improvers, and the higher the number is, the better it is, because then the viscosity variation with temperature is smaller. The way it works is that it's long polymer chains that at low temperature they just form a molecule ball, and they don't change the viscosity much. So at low temperature they don't change the viscosity, but at high temperature, when there is more energy available, they fold out like this, and then they change the viscosity by the interaction with the base oil and with themselves. So, and then you increase the viscosity at high temperature while not changing it at low temperature. Another type of rheology improver is the pour point depressant. That inhibits the growth of wax crystals. So some of the components of the oil may start to crystallize at lower temperature, so it kind of forms solid particles in the oil, and you can't use it at low temperature. So then you want to get rid of that effect, and in order to use it at lower temperatures. There are a number of other additives in a lubricant too, some different functionality enhancement additives. They are not really changing the tribology directly, but they help to keep the surfaces clean, or keep the lubricant, getting the lubricant a longer service life. So indirectly it influences the wear and the friction, of course. And one category is the antioxidants. The base oil itself will oxidate from water and oxygen coming into the lubricant, and then acids are formed, and those acids, they may corrode the surfaces and destroy the surfaces. So you really need to control the oxidation of the base oil. Then you put the antioxidants in, and the antioxidants, they neutralize this process, and so the acids, for example, formed, they neutralize the acids, but at the same time they are consumed. So after some time the antioxidants are consumed. So you must have a sufficient amount of antioxidants to not consume them before the end of life of the component or the lubricant. You have also anti-foaming agents. So the surface tension of the bubbles controls if the bubbles are stable or not. But so if you can put something into the lubricant that lowers the surface tension, then the bubbles burst and you don't form as much bubbles. And because foaming can be a big problem in a lubricant, especially if you pump it around a lot. So you must have this anti-foaming agent normally. You also have detergents, so they also keep the acids under control, but they also clean the surfaces, keep the surfaces free from deposits that could be important in an engine, for example. And you have dispergents that keeps particles they stop the, for example, soot particles to agglomerate, to form bigger particles, because bigger particles may be detrimental for the surfaces when you trap them in between two surfaces. So you keep these dispergents. They are surface active on the particle and keep the particles away from each other. And you also have rust and corrosion inhibitors, and these are surface active. They form layers on the surfaces and keeps the water away from the surface, and then you reduce the risk of rust corrosion. And of course, there is a kind of competition between all those additives. Many of them are surface active, so it's the trick. The problem for the maker of the lubricant is to have a sufficient amount of the different types of additives. So that's the formulation problem. And of course, different lubricants for different applications have different formulations. So this is a map from Lubrizol showing that how typical formulation for different types of, here you see here you have an engine oil, you may have some hydraulic fluid, and etc. So you see that you some cases you don't have that much additives. Like a hydraulic fluid, you don't have too much of some of the molecules there, while in a engine oil you have many of the components used here. In a rear axle lubricant, which is in a transmission oil, you really need, for example, extreme pressure additives, because you have a lot of sliding contacts in such an application. So that's the end of part 2, and there is one more part. So see you there in part 3. Thank you very much.